So we're working on chapter 7 today, which is on the kinetic energy and work. What we covered earlier was some study of mechanics, where we covered kinematics for a start, in which we describe motion. When we describe motion, we say we are studying the properties of a given motion. And when we study properties, we namely measure things like distance, displacement, velocity, acceleration, duration of motion. And then we proceeded in chapters 5 and 6 in studying dynamics, where we study causes of motion. And when we study causes of motion, these are basically forces. So we defined what a force is, we drew force diagrams, we studied the net force acting on a given object and how that would impact the motion of an object. And we gave this nice link between dynamics and kinematics, which is F net equals ma. So from the force, we are able to find the acceleration and then use that acceleration to find the velocity, the displacement, and the duration, and all of the kinematic properties. We studied some examples of motion, such as circular motion, projectile motion, freefall motion. And then we studied different scenarios of forces for a given object or a system of objects. And that was where we stopped, basically. And now we're moving on to our next study, which is how we can make this force. And essentially, when we want to exert a force, this can have an impact where we get some motion acting on the object. If the object is set in motion, we are going to define the work done by the force, and then we're going to check the cost of this work, which is some energy that we are going to be spending. So we start with the definition of energy, which is a scalar quantity associated with the state of an object. We said it can be transformed from one form to another. Its total amount is always conserved, and it is a scalar quantity. It doesn't have a direction. And we said, okay, when we say it's a quantity associated with the object, I can say that this quantity can also be considered the currency or what we spend when we want to exert forces, for example. And it's what the universe exchanges from one object to another to do some work as well. We said one thing which is particular about energy is that we define it by what it does, not by what it is. So we say it's the ability to do work. It's something that we have stored in the object and it can be used. Okay, we also discussed some conversions between different forms of energy. So we said, as usual, because this energy is something we are spending and it's getting exchanged, so it's going from one form to another. Let's say I want to obtain some electric energy. So I want to produce electricity. Let's say I want to produce this electricity using a generator or a power plant. Usually I would be exerting some kinetic energy because generators in particular, they operate through turbines which rotate to produce electricity. So here the kind of energy conversion is from kinetic, a rotating turbine, to electric, where we get some electric energy which we can use. Another transformation of energy which can give us electric energy is a solar cell. And in a solar cell, we're basically taking energy from sunlight and converting that to electricity. So sunlight is basically an electromagnetic radiation. So we're converting from electromagnetic radiation to electric energy. This is done using a solar cell, and so on and so forth. We have multiple examples, and What we are going to be interested in this chapter basically is just going to be the mechanical part of energy, just that. We're not going to go into the chemical and electric and magnetic and other forms of energy because this is a mechanics course. To study mechanical energy, I will start with the energy associated with motion, which is the kinetic energy K. It's equal to half mv squared, where m is the mass of the object and v is the speed of this object. The energy has a unit of joules. In fact, that's the unit for any form of energy, like even chemical energy and electric energy. All of these will be measured in joules. Now, after defining the energy, one thing that we can do with energy is we exert forces, and these forces can make motion. When a force do motion and cause motion, we are going to define this force to be able to do some work. Work is the energy that we transfer from one object to another using a force, okay? So if I have some energy transfer to the object, I will say it is doing, it's obtaining some positive work, and when energy is transferred from the object, we have some negative work, okay? So these, we covered them last time, and then we discussed a formula for the work done. As we said, if a force can cause motion, then we're gonna say that there is work done by this force. And we defined the formula for the work done. It's equal to the force times the displacement. Like we said, a force should cause motion, so I need to have one to obtain some work done. We need to have a force, and we need to have some motion. So to obtain work, I will need a force and a displacement to say that I did have some motion. As you can see, the work done is a scalar product or a dot product of the force and the displacement. I remind you of the scalar product. We gave it a formula when we studied the vectors, and we said this is equal to fd cosine phi, where phi is essentially the angle between the force and the displacement. It's not the angle between the force and the x-axis, as we did when we were studying forces. We can also write a scalar product in terms of the x and y components. So I can write that as fx times x plus fy times y. If I was given unit vector notations, this would be more convenient. We discussed the impact of the formula that we are seeing here. We said that if the work done is equal to F dot D, then if a force is perpendicular to D, the dot product should be 0, and then the work done is 0, basically. So I'll say the work done is equal to 0 if F is perpendicular to D, because I have a dot product, as you can see, and if they are perpendicular, then theta equals 90, and cosine theta is 0. And another impact we also discussed was if the force and the displacement are in the same direction, I will say the work is positive and the energy is transferred to the object. You can notice, for example, if I have this box and I'm pushing it to the right, and there's also a displacement to the right, then this force is basically supporting the motion. It's actually causing the motion, right? And if you check the work done, which is F dot D, it's going to be equal to F D cosine 0, which is F times D. All right. This will be some positive work. You will notice that if I have the other way around, if I have a force opposing the motion, such as the figure here where the friction is to the left and D is to the right. In this case, the angle between F and D is 180. And because the angle is 180, cosine 180 is minus 1. So what I will obtain is that the work done is equal to minus FD. I obtain a negative work. So notice how the work can be positive or negative, essentially depending on the angle we have. If the angle is between 0 and 90, by the way, the work will always be positive. And if the force is like opposing the motion, the work done will be negative. We will say when the work is positive, energy is transferred to the object. And on the other hand, if the work is negative, the work is negative, then energy is transferred from the object. And finally, we also discussed if I have two or more forces acting on an object, we can study the net work done on the object, which is the sum of the work done by the individual forces. So I'll check the different forces, the work done by each one, I will add them up and obtain the net work done on this object. In this slide, I also wanted to highlight situations where the work done is equal to zero. So we said one example was if the force is perpendicular to the displacement, then the work done is going to be zero. And this is illustrated in the third figure here, where I have the work done by gravity when carrying a bucket and moving it horizontally. So I'm moving this bucket to the right. You can see the displacement vector here, and the gravity force is downwards. So as you can see, gravity and delta x are perpendicular. So theta equals 90 and cosine theta is going to be 0. So W is equal to 0 in this case. Now, there are other situations where the work done can be 0 as well. You can see here, for example, in the first figure, you're pushing a wall, you apply a force, but the wall doesn't really move. So I'll say there's no work done. W is equal to 0 when there's no displacement. Remember, W is equal to F dot D. So essentially, to obtain work, the force must be moving the object. So if there's no displacement or no motion, there's no work done by the force. Another situation where the work done is 0 is when I have multiple forces, as you can see in the figure here. Each one is doing a non-zero work, but the net work is 0. So this car, for example, the thrust here is doing positive work. It's the engine force. The drag force is opposing the motion. It will do negative work. These two, if I add their work together, I'll get their sum to be 0. Similarly for the vertical directions. And then you will get W net to be equal to 0. Another way to think about it, if you check F net for this whole figure and it's 0, then W net is F net times D times cosine theta, and this will be 0 as well. So whenever F net is 0, W net will be 0 as well. And the result of that is there's no net force, the speed is going to be constant. And okay, so let's solve an example. I have here two industrial spies. They're sliding an initially stationary 225 kilogram floor safe at displacement D of magnitude 8.5 meters. So the distance here is 8.5 meters, straight toward their truck. The push F1 of SPY 001 is 12 newtons directed at an angle of 30 degrees downwards from the horizontal. The pull F2 of SPY 002 is 10 newtons directed at 40 degrees above the horizontal. The magnitude and direction of these forces do not change as the safe moves and the floor and safe make frictionless contact. So I don't have any friction. I don't have to worry about the work done by friction. We have part A here. What is the net work done on the safe by forces F1 and F2 during the displacement D? So I have here the safe is moving to the right, and there are different forces that are exerted on the safe, one by each spy. I want the net work done. When I want to find the net work done, I essentially have to find the work done by the first force and the work done by the second force, and maybe W net will be the sum of these two. Okay, so I remind you of the formula of the work done. So the work done by a given force is given by the force itself times the displacement, d in this case, times cosine theta or phi, where phi is the angle between the force and the displacement. Same thing for F2. And W net will be just the sum of what we will obtain here. So the work done by the first force, let's see, its magnitude is 12 newtons. Our displacement is 8.5 meters. And we still need the angle between the force and the displacement. Okay, the figure shows me that the displacement is to the right. I still need to see the force and the angle it makes with respect to the displacement to be able to plug in theta in my equation. Let's draw the forces. We are told F1 is directed at an angle 30 degrees downwards from the horizontal. So if I draw that, it's 30 degrees below the horizontal. So this is F1, makes an angle 30. F2 is directed at 40 degrees above the horizontal. So F2 looks like this. So I'm gonna check the angles now. Where is D? I need the angle between F and D. So I'll also draw the displacement, which is to the right. You can notice now how the angle between F1 and D is 30, and the angle between F2 and D is 40. So I'll just plug these in my equation. F2 is 10 newtons. I'll substitute these. We can calculate the work done by each force. This will be 88.3. The unit is joules. And this is 65.1 joules as well. And to find W net, I'll just add these. Remember, the work done is a scalar, so you don't have to worry about X and Y components when finding the net work. You just add them numerically. We can take a look at part B. During the displacement, what is the work W done by gravity on the safe? So I want the work done by the gravitational force, which we didn't really look at yet. We can see here, this is the safe, so the gravity is downwards, Fg or W. I can also draw it in my force
Professor, is
diagram
it
here.
0?
Exactly. So the thing is, gravity here is perpendicular to D. So if I want to substitute the work done by gravity, this is going to be equal to the gravitational force times D times cosine 90, which is 0. You can directly write it as 0, don't have to worry about it. You don't have to show your work. We're also interested in the work done by the normal force. I also have a normal force in this case because the safe is placed on the floor. So this also makes an angle 90 with D. So the work done by the normal force is 0. In part C, the safe is initially stationary. What is its speed, V final, at the end of the 8.5 meter displacement? This is basically a kinematics question. So we're interested in the speed V final. Here, I'm using the work energy theorem, which says that W is equal to delta K. The amount of work done by a force is equal to the kinetic energy that is spent, the change of the kinetic energy of the object. And delta K is none other but half mv final squared minus half mv initial squared. And this W is, of course, W net. So I'll just plug everything. I have 153 here, half times the mass of the safe is 225. The velocity is what we want, the speed v final, or what I labeled as v2. I can stick to the same labels. And the initial speed is 0, so this is 0. I can solve for v final, which is equal to calculate this. So it's going to be equal to radical 2 times 153 over 225. This is 1.2 meters per second. So, so far we discussed a general formula for the work done, which is W equal to F dot D. In the next slides, I'm going to be focusing on some special forces and extract some particular formulas which we can use for these particular forces, in addition to the general formula, which is F dot D. In particular, I want you to see the work done by the gravitational force. So the gravity force is a force we see a lot. It's actually exerted on any object we study, so it's always there. So let's take a look at how gravity is going to be doing work on different objects. Namely, I know that if the motion is horizontal, like we've seen it before, if D is horizontal, then the work done by gravity is equal to 0, because FG is perpendicular to D, so theta is 90 and cosine theta is 0. Now let's take a look at vertical displacement so that we can have a non-zero work. Namely, in the two figures here, I show you two different scenarios. One where the displacement is upwards. So you can see the difference between the two figures. Here the displacement is up, whereas here the displacement is down. I have here upward displacement, here I have downward displacement. Let's look at what gravity is going to be doing in each case. In the first figure, when the displacement is upward, gravity is down. In fact, everywhere gravity is down. So in figure B, it's also going to be downwards. In any scenario, gravity is always downwards. So what is that? What impact does this have on the work done by the gravity? Because the displacement is up and the gravity is down, then gravity is opposite to the displacement. And then how much is phi? The object's displacement will make an angle 180 with the gravity, and cosine 180 is equal to -1. So here theta is 180 and cosine 180 is -1. The result is that the work done by gravity will be negative. What does this mean? This means that the gravitational force is taking energy from the object, and it means that the gravity here is resisting the motion. It's not supporting the motion. And this makes sense. When you throw an object upwards, it's moving upwards. Gravity tries to pull it back down. It's not supporting this upward motion. Whereas, see in figure B, when the displacement is down, it's the other way around. When the displacement is downward, gravity is along the displacement. The angle between them is 0. And the result is that the work done is positive, and gravity is supporting this motion. Gravity is doing positive work, it's supporting this motion, it's giving energy to the system, and it's doing some positive work. You can see in the figure we also have some other applied force F here. So maybe it could be drag force, it could be some tension force, the object is hanging from whatever. But you can see how in the first figure, this force is doing positive work, whereas here it's doing negative work. So you can see the impact of directions of motion on the obtained work done. And we can deduce one important thing, which is that gravity will always be doing negative work when an object is ascending. So I can write this as a conclusion. And it will do positive work for any object that is decreasing in height, it's descending. Whether the descent is perfectly vertical or sort of oblique, you're going down a hill, both ways the work done by the gravity is positive if you're descending and negative when you're ascending. And that's why when you're ascending on a hill, you feel you need more energy in the ascent. This is because gravity is not supporting you, it's actually resisting you, it's taking part of your energy. Whereas if you're descending, you feel things are much easier, even easier than when you're moving on a leveled surface. This is because gravity is supporting the motion, it's doing positive work, it's spending some energy on you as you descend downwards. I also want to give you this a nice formula which you can always use as well for the work done by gravity. So in addition to this formula, which is mgd cosine phi, I'll use this formula, which is mg times delta H with a minus sign, where this is H final minus H initial. So if H final is larger than H initial, then we're ascending. So see this formula, mg delta H. Delta H is what? H final minus H initial. So if H final is bigger than H initial, then here we are ascending. And when we are ascending, W is negative. So you can use this formula anywhere. It basically just comes from using d cosine phi and substituting that with delta H, which is actually the case for gravitational force only. So this is a second formula which we can use for the work done by gravity. Now, which one do we use? How do we tell which one to use? You'll just see the scenario that you have. If you're given a distance and the angle it makes, it's a good idea to use this one. If you're given some change in height, like I tell you the object was here at h equals 0, and then it ascends to h equals 2 meters, then it's a better formula to use if you use minus mg delta h, right?
Professor?
We're gonna see where this formula comes from when we discuss gravitational energy as well. But for now, I don't want you to go through the derivation. So I'll proceed to an example. We have here an accelerating elevator cab. We have an elevator cab of mass 500 kilograms. It's descending with speed 4 meters per second when its supporting cable begins to slip, allowing it to fall with constant acceleration. And the acceleration here is equal to g over 5. So it's gravity divided by 5. During the fall, through a distance d equals 12 meters, what is the work wg done on the cab by the gravitational force? So I have put the calculations here already for you. I want the work done by gravity. I used W equals mgd cosine theta. D is downwards, you can see from the figure. Gravity is also downward, so I expect positive work. And because both have the same direction, then theta equals 0 between Fg and D, right? So I'll just plug that in my equation. So I'm plugging mgd cosine 0. Cosine 0 is just 1. I'll substitute m, 500 kilograms. D, which is the displacement. We're told that we're going a fall through a distance d equals 12 meters. So we have 12 meters here for the displacement, and we can calculate the work done by gravity. This is equal to 60 kilojoules. During the 12 meters fall, what is the work WT done on the cab by the upward pull T of the elevator cable? So here the cable is doing some work as well because there's a tension force acting on the cabin. We're interested in the work done by this tension force. Now, one issue I have here is that I don't have the magnitude of the tension force. For gravity, this was easy. I know the magnitude of gravity is it's m times g, but for the tension, I'm not given any information about the tension. Rather, I am given the mass 500, V initial is 4, and this cab is slipping at a constant acceleration, which is equal to g over 5. One thing I want you to notice, so this cab is moving downwards, all right? So this is speed. I can take the downwards direction to be positive, and then the acceleration is also positive. So I have accelerated motion here, right? Yeah, we want the work done by the tension. One thing I'm gonna do is I can try to find the tension force because the tension, the acceleration is constant. I can use F net equals ma, and F net, I'll take that along the y direction. Along the y direction, tension is positive and weight is negative. So I'll put plus T minus gravity equals ma. Okay, one issue here is you can, if you leave it as ma, a is downwards, so I'll have to put a negative sign to that when I substitute it. Or I can put the minus sign outside, all right? Up to you. So I can deduce that the tension is equal to Fg plus Ma, okay? And this is equal to Mg plus Ma, which is M into G plus A. I found the magnitude of the tension force. I can deduce the work done by the tension, okay? So I'll just repeat what we did. F net is equal to Ma. I'll take that along the y direction. One thing I prefer to do is to take the downward direction to be positive. So I'll take the y-axis to be down, and then Fg is going to be positive and the tension is negative. Or you can take the convenient method where everything up is positive, but then you'll have to be aware that the acceleration is negative. Okay, you can do that. Let's stick to the conventional basic method. I'll put the y-axis to be upwards. Namely, that's what is done in this problem, by the way. You can see how the y-axis over here, it's pointing upwards. Perfectly fine. So I'll get then T minus Fg equals, now my acceleration is also down and the displacement is also down. So I'll put the acceleration to be negative. And in the solution of the book, they leave it positive, but they plug a negative value when they substitute A. All right, you can see that in the typed solution, substituting minus G over 5 for the downward acceleration. I like to show its direction because it's a vector, just as I did for the force. I put a minus sign manually. I'll do the same for the acceleration here. I got T to be equal to Fg minus Ma, which is Mg minus Ma. So this is going to be M into G minus A. And this is, okay, I can just substitute M into G minus G over 5. So this is M times 4 over 5 G. We can calculate that.
Professor,
Yes.
I don't really understand the problem. Can you please repeat?
Yeah.
Sure.
Yeah, sure. So I'll repeat. We have here this cabin, which is accelerating downward. It slipped. So there's some slipping that's happening, and because the supporting cables are not working well, so the cab is accelerating with a constant acceleration equal to G over 5. All right. So the first question was simple. We wanted the work done by gravity during this descent. So I have this cabin, which is moving downwards. It moved through a distance of 12 meters. D is shown here. We wanted the work done by gravity. Pretty straightforward. I just substituted mgd, cosine theta. Gravity is down and d is down, so theta is 0. Perfect. I found the work done by gravity. Quite clear, right? Now in part B, we had a problem. We were asked for the work done by the upward pull of the elevator cabin. So I want the work done by the tension force, but I don't know the tension force. But because I know the acceleration and I know the gravity force, I can solve Newton's second law to find the tension. I found the tension, and then I said, okay, the work done by the tension force is simply T times D times cosine theta. I found T here by using Newton's law. Let me calculate that. So if you calculate the tension, is equal to 3,920 newtons. So I'll substitute this here, multiply by D, which is 12. Let's look at the angle that T makes with D. The tension is upwards, the motion is downwards, so the angle between them is 180. I can calculate the work done by the tension force. This is going to be, as you can see, because I have cosine 180, I expect the work done to be negative. I calculate on the calculator. I actually, yes, find a negative work done. We obtain the work done by the tension force to be negative 47,000 joules. So in part C, we're interested in the net work done on the cab during the fall. So you can see how the only forces I have are gravity and the tension force. I can deduce W net to be the work done by the gravity plus the work done by the tension. So I'll just plug in whatever I got in the previous parts. In part A, I already found the work done by gravity, which was 59,000 joules. And the work done by the tension, here it is, negative 47,000 joules. So I can find the net work done. This is going to be 12,000 joules, which is positive. And that makes sense because we have some motion and it's downwards. The net work is also down. So I expect some positive work that is done, especially that the system is accelerating as well. By the way, another way to find W net is to find F net, multiply that by D and cosine theta. But in the previous parts, we already found W by T and W by the gravity. So it's easier to just sum these up and use this method. We can use this method as well. But if in the previous part we studied F net, then yeah, that would be a good idea. But then I'll have to be doing an extra step if I want to use this formula. So I'll just stick to the easier one. So to find W net, the net work done on an object, I can use either one of these two formulas according to what's easier. In this problem in particular, I already found the work done by gravity and by the tension, so I'll just add them up. It's easier to use this method rather than having to calculate F net. Lastly, in part D, we want the cab's kinetic energy at the end of the 12-meter fall. So we want K final. That's what we want. I'll just use W net equals delta K, which is K final minus K initial. W net is 12,000. K final is what we want. Pay attention, K initial is not zero. The cab did not descend from rest. In fact, V initial is 4 meters per second. So I'll plug this as half times the mass of the cab is 500 and V initial is 4. Remember, it was given to us here in the problem. So be careful, plug this in, and the rest is just calculation. I'll find K final. This is going to be equal to 15800 joules. So you can see how in this problem, this is like a thorough work over the work done by different forces and then deducing the net work done and then linking that to the kinetic energy.